So what would be a good way to rewrite this so that it would be easier to integrate? Yeah, pull out the 2 and then make it x to the what? Yeah, you can pull out constants across integral signs. That's fine. Can you integrate x to the -3? Sure. What do you end up with? 2 times x to what power? -2. What do you have to plop out front because you want to cancel that -1/2? You want to plop out a -1/2, right? And it's going, you're evaluating from what to what? Yeah, -5 to 5. So you can pull that constant out again, and it's really just negative this, right? I'm just simplifying a little bit. One of the most common mistakes with basic definite integrals is missing a negative sign. So you have to be very, very careful here. So what is this going to be? Negative of 5 to the -2 minus what? -5 to the -2. Does everybody see that right there? Does that make sense? Is that okay so far? What is 5 to the -2? 25. And what are you adding to it? Well, actually, what are you subtracting? Excuse me. Yeah, you're going to subtract the same thing. So what do you end up with? You end up with -0, which is 0, right? Now, here's the thing. Is it possible to have a net change of 0? Is it possible to integrate something and have it be 0? Is that possible? Of course it is. I know, we're going to get there in a second, but I'm asking you, is this an answer that you could get if you integrate? Yes, you can. You would have equal space above and below. So one way you can look at it is, okay, let's try to verify this with a picture. What does 2 over x cubed look like? Did anybody graph this? Did anybody graph that to see what it looks like? And y. So to find the second derivative, what do you have to find first? Yeah, so what theorem are we going to use? Yeah, fundamental theorem of calculus part. So there's y prime. How can you rewrite that to make it easier to differentiate again? 1 plus, oh yeah, you could do it in order, sure. To the -1 is what I was looking for. But yeah, you could put it in descending order. That's fine, Hunter. But now we need to find what? Ah, the second derivative. So what rule are we using? What? Chain rule? Power rule, chain rule, right? So what do you drop to the front? -1 plus x squared all to the -2 times what? 2x plus 1. So what does this second derivative equal? The second derivative equals -2x plus 1 all over 1 plus x squared to the squared. We are interested in finding out where that function is positive. Correct? When is a fraction equal to 0? Because that's what we're really trying to find, because we want to find the zeros first. When the what? The numerator, the top. If the denominator is 0, you have problems. If the denominator is 0, you end up with things like 3 plus 4 is equal to 50. Okay? Dividing by 0 breaks math. Okay? So we're interested in when -2x plus 1 is equal to what? So what does x have to be? -1/2. So that's where the second derivative is 0, but we're really interested in finding out where it's positive and negative, right? Is the second derivative, is the second derivative 0 anywhere else? Is the second derivative 0 anywhere else? Is there any other way to make the second derivative 0? No, there isn't. So what does that mean? All of the values over here have to be what? Either positive or negative. Could it be both? Could it be like positive here and negative there?
No.
Why not? Then it passes again. It would pass through again. Or there'd be some discontinuity, right? It could jump over. But are there any other jumps in this? No. Can you ever make the denominator 0 of this right here? No. 1 plus x squared never crosses the x-axis. It's always positive. It never touches. So the only way to make the second derivative 0 is for x to be -1/2. So now we're looking at this, and we need to find out the sign on each side. What's a really easy value to the right? 0. I like 0 better. 1 is good. I like 0 better. Plug 0 into this. What do you get? -1 over? -1 over? 1. What's -1 over 1? Negative. Just because this is negative, does that mean the other side has to be positive?
No.
No. Concavity could be negative and then 0 and then negative again. That is possible. Absolutely. So what do we plug in? What's an easy value to the left of -1/2? Yeah, be careful. This is always positive, right? Denominator is always positive. Negative 2 plus 1 is? Negative 1. Negative 1 is? Positive 1. 1 over 1 is? Positive. So can someone tell me, so we know y double prime is greater than 0 when what? When x is what? Less than or equal to? Oh, not equal to. When x is less than what? Boom. You can also write that as an interval notation like this. Does it include negative a half? No, because the second derivative is 0 at negative a half, which means it is definitely not concave up. Here we go. Here's a function you've seen many, many times before. Y equals x squared. And we're going to do something nice and straightforward with it. We're going to try to find the area under the curve from 0 to 1. How did you estimate that area under the curve? How would we? What's the best way to, that you know of? Draw straight lines, break it up into what? Rectangles, right? So let's break it up into rectangles. So we could break it up into 4 of them, right? Equal spacing on the bases. We like equal spacing. Assume those are all equal spacing. Is that an overestimate or an underestimate? Overestimate. How do you make the estimate better?
Draw the triangle. Under.
Draw the under. Sure. What else could you do to make it? Draw more triangles. You could break it up into more triangles, right? So for example, I could do it twice as dense, right? I could do the blue ones right here. Is this more accurate? Absolutely. Is it still an overestimate? Yeah, I mean, these blue ones would cut down. Sorry, I got to make these go down like this. Sorry. So they would be more accurate. So how do you approach the actual area? How many rectangles do you want to take? You want to keep on taking more and more and keep on finding the answer. And what are you going to approach? The actual area. The actual area. Okay, so we're adding up an infinite number of areas of rectangles. We're adding up an infinite number of areas of rectangles. What's the area of a rectangle? How do you find it? Base times height. Okay, base times height. We are going to break this up into n rectangles. If we're going from 0 to 1, and we break 0 to 1 into n rectangles, what's the width of each rectangle? 1 over n, exactly. The width of each of these is going to be 1 over n. Do you agree with that? If you go from 0 to 1, you're going 1, and you're breaking it up into n pieces. So what's the width of each piece? 1 over n, 1 over n, 1 over n, 1 over n. Technically, as a side note, I will say you do not have to break it up into even intervals. The math will still work, but it's a lot easier when you do it in even breaks, okay? What happens if we went from 0 to 2? What would the width of each rectangle be? 2 over n. It doesn't change anything. What happens if I go from 12 to 17? It would be 5 over n. It doesn't change anything. We're just picking 0 to 1 because it's nice to deal with. So do you have to start at 0?
No.
Does it have to be 1?
No.
It can be any interval you want. What happens if you go from a to b? What would the width of each rectangle be? B minus a over n. You'll see that all over the place when you look at the proofs of these things. That's the general case. Okay, so the width of each of those rectangles is 1 over n. But to find the area of a rectangle, you need the base times the height. So you'll notice that when I drew these rectangles, it's always the right corners are the heights. Do you see these? How it's the right corner of each? Okay, so we'll call this one x1. If I started at 0, how far over did I go? I went over 1 over n. So what x value am I at? I'm at 1 over n. If I go to the next one right here, that's going to be x2. I've gone 2 of them, so I've gone 2 times, which is the same as 2 over n, right? It's going to keep on going. 3 over n, 4 over n, 5 over n, 6 over n, all the way up to, what's the last one?
1.
Yes, but what's another way to say that? N over n. So do you see how we're incrementing there? So the first height, so the height is just the function, and what do you plug into the function? All of those x values. What is x sub I going to represent? All of these x values. What is x sub 1? 1 over n. What's x sub 2? 2 over n. X sub 3? 3 over n. And what's x sub n? N over n. So what are we doing? We're adding up all these rectangles. So what's the area of the first rectangle? 1 over n times the function evaluated at what? The function evaluated at 1 over n, which is x1, right? And then what do you add to it? Well, the next width times f of 2 over n, right? And what does it go up to? 1 over n times f of. There's a lot of repetition in there, right? What can I factor out of each of those? 1 over n. So I end up with 1 over n times the function evaluated at 1 over n plus the function evaluated at 2 over n plus all the way up to the function evaluated at n over n. Remember, though, that this is just the width. And what are each of these? These are the heights. And how many rectangles? What do we want to look at this as n goes to what? Infinity. So we're really looking at this right here. The limit as n goes to infinity, if I can write that, of 1 over n times that thing right here, all the heights. I just don't want to write it again. Now that's really long to write, correct? So instead, that exact same thing is written like this. The limit as n goes to infinity of 1 over n times the summation of I equals 1 to n of f of x sub I. What is x sub I in this case? Well, plug in 1. X sub 1 is 1 over n. What's x sub 2? 2 over n. This looks pretty complicated, but it's far less writing than writing this out the entire time. Do you understand what's going on there? Again, what does this represent? What does this part represent? What is that? What is that? That's the width. And what's this? So let's pull it out. The limit as n goes to infinity of 1 over n times what? The summation of I equals 1 to n of what? What can I do to I cubed over n cubed? What could I turn that into? I over n to the what? Cubed. So if I is 1, what does this become? 1 over n. If I is 2, what does the next one become? 2 over n. Then what? 3 over n. So this right here is the area under the curve of what function from 0 to 1? X to the what? Yeah, this is the area under the curve x cubed from what to what? 0 to 1. It tells you that, right? Do we have a different way of writing Riemann sums? The integral, oh, that jumped. The integral from 0 to 1 of, can you do that out in about 30 seconds? What's the antiderivative of x? 1/4 x to the, from what to what? From 0 to, you go lower to upper, 0 to 1. So what's that equal? 1/4 minus 0, which is? There it is. You've redone this. You've rewritten it to this, and you've recognized this as, this is the Riemann sum representation of the integral from 0 to 1 of x cubed.
Can you just explain, like,
Hold on, let me point you up.
over n cubed?
What? Limits without doing integration. Here's what it looks like. So first of all, what is this for x squared? That right there, you have the limit as n goes to infinity of 1 over n times, what are you adding up? 1 over n squared plus 2 over n squared plus 3 over n squared all the way up to n over n squared. You agree with that? It's nice. What can I factor out of each of these?
1 over n squared.
1 over n squared. It's in each of them, right? So it's going to become limit as n goes to infinity of 1 over n to the what? Cubed times what? 1 squared plus 2 squared plus 3 squared all the way up to n squared. Nice. Have you ever seen this before? It's the sum of n squareds. Probably. The sum of n squared is equal to n times n plus 1 times 2n plus 1 all over 6. This is something you have to memorize. You might want to write this down separately. How can we rewrite this now? We now know that it's the limit as n goes to infinity of 1 over n cubed times n plus 1 times 2n plus 1 all over 6. This is going to infinity, right? What's the degree of the top? The degree of the top.
N cubed.
Cube, 3. What's the degree of the bottom? 3. The degree of the top is 3, and the degree of the bottom is 3. Is it good that it's the same power?
Yeah.
Yes. If the degree on top was bigger than the degree on the bottom, that would be a problem. Why? What would the limit go to? Infinity. If the degree on the bottom was lower than the degree on the top, it would go to 0. We are trying to find the area under the curve of y equals x squared from 0 to 1. Is that equal to 0? No. Is it infinite? No. So is it a good thing that the powers are equal?
Yeah.
Yes. Okay. Have you done limits like that before?
You have
Yeah, you have. Find me the limit. Go.
x squared.
X squared. So you end up with x squared minus e to the x, because what's the integral of e to the x? Negative 1 to 0. This is where the plugging in is really important. So you end up with 0 squared minus e to the 0 minus negative 1 squared minus e to the negative 1. What's e to the 0?
1.
So you end up with negative 1 minus, what's negative 1 squared?
1.
1 minus 1 over e. So what do you end up with?
Negative 2 minus 1.
Isn't negative 2 plus?
Oh, plus.
Plus 1 over e.